field. But I'm on leave of absence at the moment. And I've been for the last 2.5 years working for Amazon, where I'm a director of machine learning, and I work in the supply chain. And the reason for that move is I'm very interested in it's nice that we made all these algorithms. We spent 18 years trying to persuade everyone to use them. Now they're using them. A lot of the issues are in how they're deployed. But today I'm not going to talk to you so much about that, which is an interest of mine, but talk to you about Gaussian processes, which are a particular approach for machine learning that we saw coming up in a few of the early lectures. But in common with some of the others, first of all, I should say there's this book, which is now 13 years old, but still a great book, and it's available freely online as a PDF. I'm not going to follow the way they introduce them so much, but it's just a great additional resource if you want a textbook. But in common with a few of the others, people ask for definitions of machine learning at the beginning. So let me just give you my little sense of what machine learning is, because I'll use that to motivate why I like Gaussian processes. So almost every talk I give starts with this. It's not really a formula. It's a sort of the combination of data and model leads to predictions. Now, that could be the underlying formula of a number of fields, including statistics. But the particular focus of machine learning has been that we like to make high-quality predictions, potentially sacrificing interpretability. Statistics cares more about interpreting whether a data set means something, like whether you can statistically show that a drug is effective through looking at data. And when they do use models, they tend to use models for interpretability purposes. And that's a very worthy thing to do. But in machine learning, I think you can't get away with, so we're given data, and we're interested in combining it with a model. Now, for me, so data is observations. It could be actively or passively acquired. So in something like robotics, your data is actually, you decide where to select your data points. In stats, that's called experimental design. In machine learning, we call it active learning. The model, which is your assumptions. And that could be based on previous experience, so other data. So that's sometimes called transfer learning. Or beliefs about the regularities of the universe. I think that's the fundamental thing you're putting in your models very often, how you think the universe works. Like, most of you would be pretty surprised if I were to disappear from this side of the stage and instantaneously reappear on that side of the stage. And that's a smoothness assumption. Okay, that's one of the regularities of the universe. So we like to include smoothness assumptions. I mean, actually, most of these things have underlying physical reasons. So laws of large numbers often lead to smoothness assumptions. And we use smoothness assumptions a lot. And in fact, one way of looking at what Gaussian processes do is there's sort of, broadly speaking, a smoothing algorithm. And then the prediction, I don't think of prediction just in terms of the classical way, like is it a yes or no, but I think the prediction is, I even think of it, I conflate that with decision a bit, personally. So that could be a decision on an action to be taken. Sometimes people separate the prediction as a probability distribution. I think this is a good thing to do. And then after you get the probability distribution, you might need to combine it with something else before you make a decision. But just for the purpose of this equation, they all come together. So I think reinforcement learning, supervised learning, unsupervised learning broadly fit under that. So now to combine a model with data, very often we need two things. One of those things is, and this isn't universal, the thing at the top is supposed to be universal. This is broadly an approach to doing it, a prediction function. So the prediction function is what people are talking about as neural networks. That's a commonly used prediction function, but you can use linear models, you can use all sorts of models. And an objective function. So that's the thing that measures the mismatch between what your predictions are and what you're seeing in your targets. And you typically minimize the objective function. Now, two broad approaches are commonly conflated, and they're separate and should be kept separate. One approach is that you write down a probabilistic model. And your probabilistic model defines your objective function, and you fit that by maximum likelihood or using Bayesian techniques. That's quite different from the other approaches, which is where you write down a cost function that you typically want to minimize. So when you write a cost function you don't want to minimize, you believe that that's maybe actually the cost of misclassification. So I work in the supply chain in Amazon, so and you get a lot of operations research scientists. In operations research, very often you're quantifying costs through money, through the cost of a decision, an incorrect decision, in dollar terms. Lagrange multipliers often have interpretations about a step change in increasing the capacity of your supply chain, or how much and a dollar cost associated with that step change, a dollar profit you will get from that. We don't see that so much in machine learning, but we shouldn't forget about it. And cost functions, I think of things like that as money. I like to keep those two ideas separate philosophically, but they come down to the same thing very often mathematically, because sometimes people use a cost which is the quadratic error. Now, has anyone ever paid a quadratic cost for missing something in actuality? I don't think it ever happens. It's like, I don't know. How much penalty do you lose by missing a train? Is it quadratic, or is it the actual amount of time you're losing? Very unusual to pay actual quadratic costs. Why do we use it? Numerically simple. So it leads to a lot of tractable algorithms. But in the probabilistic perspective, it implies things are Gaussian. And I think that it's far better justified through appeal to Gaussianity assumptions, which are relatively common. So you get to stand here in front of people, you have to give all your thoughts about the world. So I really regret the fact that certain people in the field, when machine learning became successful, started readopting this term artificial intelligence. I think it was dead. We should have left it dead. And we could have just said we're doing machine learning. But, okay, so having regretted that, I try to be a positive person. I like to complain a lot, but then also look to what the utility of a term is. I think when I talk about AI, I tend to think that machine learning is sort of the mainstay of modern artificial intelligence. And what I think of as AI is all those sort of things that we used to not be able to do, that humans could do, but we couldn't get computers to do. So I think in particular of sort of speech recognition and language translation and recognition of things in images. And machine learning is a mainstay of AI because of the importance of prediction in that. In old-fashioned AI, then it wasn't sort of acknowledged that you were going to use data to that extent. And the big changes machine learning has driven that. Uncertainty is also a critical part of that. So I think uncertainty, there's a number of things I think Gaussian processes would be more popular if they weren't called Gaussian, if they were called something funky, like, I don't know. Well, I don't know how to pronounce, so you can tell me here, people can tell me, how do you pronounce Krieg? Krieger. So actually, Gaussian processes were developed by a South African mining engineer. But the theory was developed by a guy called Matterhorn in France, in Paris, at the École des Mines. And he found this sort of heuristic thing that this guy was doing to, I think, prospecting for gold, actually. Because there's a term known as the nugget term, which is about whether you find your minerals in nuggets. And so Matterhorn called it criage, I think. Yeah, I don't know how you pronounce it in French. So unfortunately, it's just not a great, I don't know how to pronounce the Afrikaans way. I don't really know how to pronounce it the French way. But it would be really great if you'd had a really simple name which we could all use, because it's misleading. People think Gaussians are boring. I think Gaussians are boring. Well, I thought Gaussians are boring. I thought Gaussians were boring because I had to do them at school, and we had to learn the formula for the standard deviation. It didn't seem like proper maths. But they're not. They're super interesting. I hope I'll persuade you that. So neural networks are just a prediction function. And they're just a way of trying to incorporate certain regularities like translation invariance. And they're very complex and funky looking because it's difficult to incorporate such regularities. I mean, much harder than it should be. It's just translation invariance. It's not that bigger of a deal. But to incorporate it in a function where the output of the function is invariant to input that is translated turns out to be hard. And that's one of the challenges we face with modeling. If you go back to 1801, when people were modeling, they didn't build models that weren't motivated by physics. So people like Gauss and Laplace used the laws of planetary motion to build models that they fitted to astronomical data that were basically based on Newton. Yeah? And there wasn't a separation between the fields. You wrote down your model because you knew the physics. What's happened is, as physics has got more and more complicated, you write down Navier-Stokes equations, it's pretty hard to combine them with data. So it's very hard for some of the more complex physical assumptions we have to combine them with data. And so what effectively has happened is there's two worlds of data modeling. One is where you spend a lot of time on the physics of it, and then you have a lot of trouble incorporating data. And then the other one, like the machine learning statistical modeling side, where you're writing down simpler, more mathematically tractable functions, but they don't include such hard physical assumptions. And in order to continue to allow them to fit to data, to fit them into these algorithms we use, they have to be relatively simple. So there's this interesting tension between there. And although neural networks seem complex, they're not complex compared to a climate model. I mean, they're just not. I mean, they're way simpler. Okay. So what goes on in a neural network? Well, this is my little representation because I want to map it into, I'm going to try and take you from neural networks to Gaussian processes in a way that actually the Gaussian process book does as well. So I'm interested in prediction functions, and I like to use matrix notation. So this is a vector in a product. So what I have here is I have my inputs, and I have a matrix of weights on an input layer, and I have some basis functions. Now, Shakir's gone now, so I can disagree with him while he's away. He said that's an inverse link function. I totally disagree with that. I'd say that's a basis function. Inverse link functions are things that come on the output of the model. But I'd say in statistics, we call that a basis function. But in neural networks, we call that an activation function. And models like this have existed. They're as old as the hills. Gauss would have been familiar with them. But the basis functions Gauss used were inspired by physics. They were inspired by Kepler's laws. And the parameters Gauss was interested in would have been like the parameters of the orbits. But Gauss would have fitted models like this, and he would have done them by least squares, or so he claimed in his priority dispute with Legendre. So the big difference with neural networks, though, versus classical statistics is in statistics, you write beta instead of W. Okay? Certainly here. Now, I like that separation because it means when I write beta, I'm not going to write it in these lectures, but sometimes I pretend to be a statistician. And when I write beta, it means I care about the value of the parameters in terms of I have some interpretation associated with it. When I write W, I don't care about the value of the parameters. They're just a means to an end, the end being the output of the function, my prediction. So I'll give you an example of where they come up in statistics. You might use a linear model such as this. This is a classical linear model, but you can extend these to generalized linear models where you do put a link function on this left-hand side. You might use that to try and predict disease rates. Okay, so you might be interested in what things affect heart disease. And you might be looking at inputs. Your X might be cholesterol. Your X might be whether you smoke or not, whether you drink or not. And in a linear model, these basis functions would not exist. There'd be no parameters here. It would just be W transpose X or beta transpose X. And each of those beta weights would be indicative of whether one of these effects was sort of protective or harmful towards your heart disease. And if you do a course in linear regression in statistics, you'll find it's like a 20-lecture course. That's not because they're thick. It's because most of the course, the algorithm for linear regression is just lecture 1. Most of the course is understanding the interpretation of what those beta coefficients mean and when they're valid. Because you're going to use those coefficients to advise a government whether an intervention with mosquito nets across the whole of East Africa, which cost hundreds of millions of dollars, was worthwhile. And so you have to be careful. People typically have been less careful when they're worried about ad clicks. Okay, but these models are broadly the same for a sort of one-layer neural network. The only difference is that the big innovation which caused me to join the field back in 1996, although I was already 10 years behind, was backpropagation, being able to optimize the basis functions as well. And that isn't even a big idea. It's just statisticians worried less about it because their basis functions were interpretable objects that came from physics. Our basis functions are just things we're using as a means to prediction. Okay, I said all that. said that too. Now, what I want to do is take you down a path that was the path I was led down when I joined the community in 1996 to do these very radical, exciting things called neural networks that were really wonderful and going to change the world. And I was very strongly influenced by this gentleman, whose name is David Mackay. He unfortunately died last year at only the age of 46. He's one of the most influential researchers in the early days of machine learning. I think many people in the audience here have been influenced by his work. And what the decision was is that in these models, you typically optimize. Well, in statistics, you optimize that. And in machine learning, you decide to optimize the objective function with respect to that. And the decision that we went down was that instead of that, we're going to integrate them out. We'll take what's called a Bayesian approach. Now, let's see if I can insult someone else. Where's Sebastian? He said he was a Bayesian. I think it's weird to say you're a Bayesian. It's like saying you're part of an odd sect or something like that. And the reason it's weird is because Fisher invented the term to make it sound like that, because Fisher didn't like Bayesians. Fisher was a great statistician, but he didn't believe in models. He thought you should just look at the data. He thought the data should speak, and if you brought in subjective modeling, then that was dangerous. And I think he was broadly right for a lot of statistics. Unfortunately, how far that takes you is limited. That gives you like randomized controlled trials. At some point, you have to start getting subjective and modeling. And if you are going to be subjective and modeling, a really good way to do it is with probability. Now, that makes me a Bayesian in the same way that I'm, okay, I don't know which section is our audience. I'm either a Leibnizian or a Newtonian for using calculus to deal with rates of change, okay? Probability is just the calculus of uncertainty. That's it. You don't have to belong to a sect or call yourself a Leibnizian in order to use it for that purpose. Sometimes you use it in slightly different philosophical ways. So sometimes there are things that we put probabilities over that some people say, well, how's that a probability? That's where all the argument is. Yeah? All the argument is over whether a sort of a known parameter is valid for the probability over it. To be frank, we don't have to care about that. And it's an argument that I think is almost dead. It's an argument that belongs 100 years ago. But you'll see its echoes throughout modern parlance. But when I think about probabilistically, so probabilistically, this is what I'm interested in. This is my notation here. This is the holy grail of machine learning. I'm typically given, I'm splitting the world into inputs and outputs. So I don't always do that. So I'm given some x's. And I want to make a prediction about some new test output y star. And y is my training observations. So the nice thing about probability is it's very easy to write down complex models in a very simple form. So this model is saying that I'm interested in the probability distribution over some test output I'm interested in. That might be the price of a Big Mac in Tokyo. Given some training data, which is some things I know, which might be the temperature here in Cape Town, or Stellenbosch, sorry, and given some other inputs, right? Now, we're not saying anything more than that. Typically, we don't ask such bizarre questions like that. We sort of say something like the value of some MNIST model output, the label, the class label, given the training labels and the pixel values. But that's a pretty uninteresting question, really. I mean, how many humans, what I think fascinating about humans is we become so obsessed with these tables of numbers we're given that we've built a load of machine learning methods to deal with tables of numbers. But like when does that actually happen in your real life? When are you actually acquiring data that's on a fixed vector? Well, you could argue maybe your visual system is, but I don't think it is because you're saccading the whole time. You're picking up snippets the whole time. So you're getting bits of information which, somehow you choose to interrelate, somehow you have a model of, and we'd like the computer to be able to do that. And if we wanted to do it probabilistically, that's how you write down such a probability distribution. The problem is that doesn't tell us anything. That's just expressing what we want to do in a little bit of notation. But importantly, notice there's no independence here. Right? Now, people just live and breathe independence assumptions, which is very weird. And they say, I'm going to assume my data is independent. They don't mean that. That doesn't mean anything. If I assume my data points are independent, I can't learn anything about one data point given another. Right? So it doesn't mean anything. What do they mean is, they mean, and we'll see that coming up in a moment, that you assume conditional independence of your data given the parameters of your model. What you mean is, and this came up, I missed unfortunately the causal debate, but noise is typically independent, right? And what you really mean is you're saying, well, you're not, sorry, noise isn't typically independent. You're saying, you're making an independence assumption about your noise. You're saying, given the parameters of my model, I expect the only probabilistic things to occur is independent random noise. And that idea goes back to Laplace when he was doing observations, and Gauss used it as well, and saying, oh, the reason that my model of the universe doesn't exactly fit the data is because every single point I've been given has been corrupted in some small way, and I will assume that those corruptions are independent. And that's what you mean when you assume independence, something which we very sloppily refer to another way. But if data were genuinely independent, you wouldn't be able to say anything about it. So actually, the typical way that we deal with that in the weird Bayesian cult is to use integration and multiplication. I mean, there's nothing odd going on here. So that would be like what we would do normally is we'd write down our neural network in the form of a probability distribution. We'd be embedding it in there. So that's the probability of an output data point given an input data point and our parameters. And that's typically assumed to be independent. I'm only showing one data point here. And what we typically want is, we want some, in the Bayesian world, the idea is, or one idea is, this is one route to building this probability distribution. It's not the only route, but it's one very commonly used route, is that I place a prior distribution over my parameters, which leads to this posterior distribution over my parameters. So given my training data, I have some distribution of beliefs about what my parameters are. And it's relatively easy to write down using Bayes' law, otherwise known as the product rule, what this posterior is in terms of your likelihood. And that's the very typical way we form this prediction. And almost when someone's saying that they're going to be Bayesian, you assume that that's what they're going to do. And I want you to get rid of that out of your head. I want you to sort of think that, no, it's just one way of doing this. It's just one way of doing this that says, and this is why it's a parametric model and why it's a dangerous thing. It says that the information about my training data, basically this is a bottleneck, comes only through these parameters. And there's a fixed number of parameters, and I decide that number of parameters at the time I build my model. And that's why parametric models are a bad idea. Because in practice, that's not what you want. In practice, you want to be able to add capacity to your model as you go, and that's what non-parametrics allows. I'm not going to go too much into the detail of that, but this is the classical parametric way of constructing that probabilistic prediction that we want. Okay. So in this case, if it's a neural network, then my W matrix contains the input and the output weights. So what people are trying to do with these crazy Bayesian neural networks is build variational approximations to this distribution here. That's what's going on at the moment. That is what I did in my thesis in 1999, 2000. And the techniques are much more advanced and more interesting now, but I still don't want to do it again. It's a nightmare. Not wanting to do that was why I moved to Gaussian processes. So in this thing, this is known as the likelihood of a data point. That's sort of been mentioned already by Shakir. And we normally make that an independence assumption that I spoke about. But to be clear, this independence assumption, notice it's conditioning on two things. If it weren't conditioning on that, then it would just be, the world would be meaningless, right? Because I couldn't tell you anything about different y's in this, because these are separately indexed. So it's just a product of distributions, and you take the log likelihood, and no distribution is saying anything about any others. Having W in there is what makes it work, that conditioned on W, the parameters of the model, we have a joint distribution. But that kind of shows that W is your weak point. So W needs to include everything you're interested in about all the communication between the world of training data and the world of test data has to be fixed in W. And once you've sort of pinned that down, you're kind of beholden to it, which is a vulnerability of the way we do machine learning. Now, the way that this looks like, bringing back in the prediction function, in a probabilistic framework, if we're doing regression, we might use the Gaussian distribution, invented, of course, by de Moivre and Laplace. It's called the Gaussian distribution because Gauss used it, and he credits Laplace. Gauss used it, though, for justifying least squares. So when you do the log likelihood, you get this quadratic form that motivates least squares. And he recovered the lost planet series, he says, in that way. But he says he did it in that way as part of a priority dispute with Legendre, who also proposed least squares. Now, going beyond that, this also, Sebastian mentioned this, is like what happens when you start looking at things like generative models like GANs. You can do the same thing, you just start, I mean, this is one way I really like that way of building generative models. I've spent a career doing it, and I'm going to touch on that in the next section, not so much in this section. I'm just going to show you this and throw it away. If you put prior distributions over what the input to that system is, you can come up with some very interesting probabilistic models. The GAN is trying to do the same thing, but not using the maximum likelihoods. But variation autoencoders are doing this, where you put priors over the inputs. But that's just an aside, because for the moment, I'm just going to focus on supervised learning. But to me, these are, if you're doing probabilistic inference, this is what you're left with. You're left with data and your model, which gives a joint distribution between how your real-world data, so the ones you want to make predictions about, relates to the input data you're given. And this is how you answer questions. When you answer questions in probability by conditioning. The problem is that doing this involves integrations, defining models, and all sorts of other things. But in principle, it's simple. So in principle, it's much simpler than all the maths we do to do IID, but we have to go to something like IID to make this sort of tractable. So other things, I mean, looking back, Shakir's already done a great job at this, but the sort of things that are being neglected now, which will definitely come back into prominence, are things like writing that decomposition down in other ways. So a Markov chain is one where you're not making independence assumptions conditioning on parameters. You're making some sort of chained assumption. And the reason this is good is because it turns out, and it's kind of quite easy to see in this case, instead of like before where we had the independence assumption P of yn, P of yn minus 1, so on and so forth, without the conditioning, right? That's what made that tractable. Everything was independent. Now they're only dependent on one other point. And when you take logs, everything turns into sums, and it's all tractable, and people worked that out ages ago. A conditional decomposition of this distribution is one way of getting tractability. And something that's related, that I'm not going to talk about, but strongly related to Gaussian processes, is Gauss-Markov random fields, which are spatial models that decompose these joint distributions into a series of conditionals. And that's a great trick to make things tractable. The problem with those things, and this you can't even see it because back in the day, this is how you would approach machine learning. You try to build a graphical model, and then you would even learn the structure of these graphical models if you're quite advanced, and someone's trying to predict some, I can't pronounce these words, perioperative risk of Clostridium difficile infection following colon surgery. And then you get this very complex structure. So the whole idea, I love Bernard's work and everything else that we heard about on causal inference and writing down a causal structure. And if I just know that this is related to this, fantastic, I can start making judgments about what to measure, how to intervene. Well, how does that work for this? What's gone wrong here? Well, what's gone wrong here is when you're trying to make these decompositions of your joint distribution into a series of simple distributions, each of these now has to be parameterized, and typically people might use a conditional probability table or something for that. some simple representation to give us this distribution, that those distributions tend not to be very rich. And as a result, as you start interrelating all these variables, you tend to need a lot of dependencies in order to describe the rich underlying structure of what's going on. And you lose, you started out, it's that classic way, you started out with this wonderful thing because you were going to do interpretability and everything else, and you end up something that's not interpretable and isn't particularly powerful predictively. Now, my philosophy is that just because that's true, you don't throw this approach away. And one of the things I'll be talking about next session is what happens if you start using very complex models to represent these conditional distributions. I think that's a very promising direction. And the complex model I'll use is a Gaussian process. Okay, let's see. We go back to there. So, the way that we would do an analysis in our weird Bayesian sect that uses probability is we would put a prior distribution over this parameter. That means before we see the data, we make an assumption that the W is drawn from a particular distribution. Now, this is the sort of thing that gets people's knickers in a twist. They don't like this. They say, well, but where does the prior come from? Well, where does the model come from? I mean, to me, it's a nonsense question, right? It's a model. It's just part of constructing the model. And you can show certain situations where, your likelihood choice and your prior choice, they interact. I mean, the truth is, where does the model come from? The reason they ask that question is because it's very common in Bayesian statistics to take models which have a likelihood that's based on a classical, well-tried and tested statistical approach that people feel very familiar with. So familiar with, they don't even remember they're making assumptions anymore. And then you have to add in a new prior. And then they get their knickers in a twist because they weren't taught about that as undergraduates. But it's the same problem. I mean, it's not adding any more problems. It's just you're just trying to specify a probabilistic relationship between your models. And that is a fraught thing. It's difficult to do whether or not you're putting priors in or not. But you can do things, as we'll look as we start doing later with Bayesian inference, to show what it means. So what I'm interested in is believing my data is given by some prediction function, which is, for the moment, given by that object there, that one-layer neural network, plus some noise. And I'm also making an assumption about the noise. Now, it's very interesting if you read old work by Laplace. In effect, what Laplace is doing is he's putting a prior distribution over the noise level. It's just part of your model, though. I mean, it doesn't, we call that a likelihood. But really, he's saying this is what I think is going on in the world. This is some corruption I see. Something that's messing me about. And I'm going to assume that that's independently distributed. And that's what we mean by an ID assumption. Now, while we're here, there's a strong philosophical difference between the way we tend to use Gaussian processes in machine learning and the way they tend to use them in spatial statistics. They're very widely used in spatial statistics. They'll come up a lot. In spatial statistics, I would get the model to this point. This would be my linear model, probably beta transpose something I'm interested in, plus some corruption. And then I would say, but it's ridiculous to assume that the noise is independent. I expect noise to be spatially correlated. And then I would make an assumption that says that's not independent, that has some dependence on spatial location. But it's my noise, right? And I want to get rid of it. If I was using all the factors in my model that I should be using, it would drive down to 0. But I often can't do that, so I have a spatial noise component. Now, in machine learning, that's not what we do. We think of this as the Gaussian process, our prediction function. And that's what a Bayesian approach would be. So that's kind of maybe where some would argue you're being Bayesian versus... So someone like Peter Diggle, who is not a Bayesian, is just a fantastic statistician with an expert in epidemiology, would happily put a Gaussian process prior on this, but probably would be more reluctant to put the process prior on the thing he was interested in, which is a set of parameters relating to the disease he's interested in. I speak for him. He's not here, so we can't disagree. Okay, so I mentioned Gaussians a few times. So Gaussians are really, really important. but not for the reasons that people think. Everyone thinks the mean's important, but as it'll turn out, it's the covariance that's important in a Gaussian. The mean's very boring. The mean's what you're using at the moment. When you're fitting a neural network for regression, you're effectively fitting the mean of a Gaussian process. That's very boring. What you're interested in is the covariance. So this is an interesting property of the Gaussian, which I guess we get shoved down our neck so early on that we don't even think about it, and that's that the sum of Gaussian distributed random variables is also Gaussian distributed. And I think when we're taught that, we just think that that's unremarkable, because it just seems, well, that's nice. But of course, that's not true of almost every other distribution. It's true of certain gammas, it's true of Poissons. And of course, central limit theorem tells us that as long as distributions have finite variance, as long as however y is sampled has, and the variance exists, as we sum different y's together, they tend towards Gaussian. So that's why Gaussians are useful, because, and Laplace also, I think, proved the first version of a central limit theorem. So why he's not credited on the Gaussian distribution, I don't know. Anyway, it's because everything's invented by Laplace. So this summing of variables together also leads to a Gaussian where the mean sum and the variance is sum. Now, you may have heard that before, but that becomes out to be very interesting because it has this very interesting consequence. When we combine it with this property, which is not so interesting, it says that if you scale a Gaussian variable, then the result of scaling it is also a scaled Gaussian variable. But that's true of lots of distributions. Scaling many distributions is just the scale parameter, right? So this is less interesting. But with this other property of the Gaussian leads to this very interesting thing for multivariate Gaussians. So if x is sampled from a multivariate Gaussian process. So a multivariate Gaussian process is defined by a mean vector and a covariance matrix. If x is sampled from and x is a vector, sampled from a multivariate Gaussian process, and we define y to be some affine transformation of x. So this is matrix multiplication. Matrix multiplication is just a cheap way of doing a load of multiplications and additions at the same time. So all that's going on here is the top row of this matrix is being multiplied individually by this column of matrix, each one being scaled by a separate element of w, and then you're summing together to get the next element. So everything scales and sums. And that means that when you look at multivariate Gaussians, you get this. The y must necessarily be drawn as a Gaussian, with the mean being given by W mu and covariance given by WC W transpose. Now, if you go back to the univariate case, you see it was W squared, sigma squared there. But if you look at this case, what's going on is you're applying your affine transformation to the mean, and then because the covariance is like the square of the standard deviation, it's also in the multivariate case, it's the same. The sort of thing that exists in the space you're interested in is the half, the square root of the curve, the covariance, which would be a Cholesky factor or some kind of underlying eigendecomposition of your covariance matrix. That's the thing that gets multiplied by the affine transformation on either side. Now, you might think that that's not very interesting, but what is difficult about high-dimensional integrals? Everything. But we just did one. So this is, by definition, a prior distribution over x. This is a probability of y given x. And this is a probability of y. So what I did is I did the sum rule of probability with this property, where I've gone from a p of x, a p of y given x. This is just the mathematical. I mean, I can add noise to it, as I will do later. And this is the p of y, and it's a one-liner. High-dimensional integration is, I mean, how many processor cycles we're using to do that worldwide at the moment is just absolutely extraordinary. So it's such a weird property because it gives you this ability to do very, very high-dimensional integrals. So high-dimensional, I'm integrating out x here. That's what's going on. This is multiplying this probability by the probability this implies by the probability of this is the product rule, and integrating out x is integrating something the dimensionality of x. I haven't specified the dimensionality of x. So it could be infinite dimensional, kind of, countably infinite, and that's still a one-liner. That's the beauty of Gaussian processes. And Philip Hennig, there's a tutorial. We do a Gaussian process summer school every year, and every year we typically invite someone new to give an introduction to Gaussian process, which is great because so many different people use them, you get different perspectives on what they are. And I guess this emphasis is coming from a tutorial that Philip Hennig did, where he basically said the reason we love Gaussian processes is because probabilistic inference in Gaussian processes is just linear algebra, which is just a great point, you know. And we built machines that do linear algebra already. So we just get to use those. Or for neural network people, it's the activation of a neuron or something. Yeah, but GPUs do linear algebra already. Okay. So linear Gaussian models are very easy to deal with. And we can also extend that to make that, we can add that noise back in. So we can have this thing here, which is just a multivariate regression. So this is my f of x this time, but it's a multivariate f of x, multivariate output, multivariate input, and this immediately gives me the y. Now, actually, so in this case, I've actually chosen to integrate over x, not w. This model is known as probabilistic principal component analysis, or it's known as factor analysis, depending on how I set c and sigma. This is a very, very widely used probabilistic model, and it's all linear Gaussian. Okay, now, problem is we don't just want to do linear models, but we want to do nonlinear models. Now, in particular, what goes on in a Gaussian process, and this is sometimes a cause of confusion, they're typically referred to as linear models still. The reason they're referred to as linear models is because if you look at the parameters, ignore the parameters in here, these parameters are appearing linearly. But they give nonlinear regressions because the inputs are appearing nonlinearly. So in simplistic ML terms, we'll often say, oh, it's a nonlinear model. But any statistician or mathematician worth their salt would talk about it as a linear model. It would have to be, this model is nonlinear in those parameters, but it's linear in those parameters. So when people are talking about linear models, they mean linear in the parameters, not linear outputs. They also... Another confusion is generalized linear models. This isn't a generalized linear model. It's a generalized linear model if I put a link function here and start doing Poisson regression or classification or something like that. So just how things are interrelating to my understanding of statistics. But how we build these models that are nonlinear in the outputs is we use basis functions or activation functions. And you could, of course, write down that you've got a sigmoid or whatever else. But the classical thing to do in statistics is just to refer them to as a elements of a matrix, and this is called the design matrix. So the design matrix has n rows, and it's got h. I've used h for hidden values, but often people use m or k for number of basis function in the model. And you have in the linear model, this h is equal to your input dimension, but in a nonlinear, in the inputs model, it's equal to the number of basis functions or the number of hidden units you have in your data layer. So if you're used to neural networks, each row here would be for each data point the activation of each neuron. Yeah. But in statistics, this form is called the design matrix. I'm emphasizing that because it's n in that direction. And it's the number of basis functions in that direction. Sometimes when people implement this, they do it the other way around, or when they do math, they do it the other way around. Of course, it doesn't really matter. Math still works. But it's very confusing if you do it that way. It's like, you know, you make a choice to either drive on the left or the right. If some people drive on the left and some drive on the right, it doesn't work. So I like to advocate, please write these matrices as the statisticians chose to do. Okay, so that gives us the ability to write down a so-called matrix representation of a neural network. So now in this case, my vector phi of x is a vector taken from one row. Now, my vectors are always columns, right? So it's not a row vector in the next bit. Once I've taken it out, it's a column vector. So this is just a little matrix way of writing down what the output of my neural network is. So f of x is my prediction function. When I corrupt it by noise, I now refer to it as y, the output of my neural network. Now, if I can actually rewrite that for all my training data. And this is a nice trick. It makes the math easier once you do this. So using this design matrix layout, I can multiply that design matrix by the vector of weights in the output layer. So for each, if I do that, once I've done that, I'll get that vector times that vector, one output there. Oh, success. And in the end, what I get is my vector of the observations at every single training point, which I just refer to. I've dropped the conditioning on x here. X is embedded in this phi matrix here. And epsilon now, this is a noise observation for one point. Epsilon is sampled from my noise distribution, so independently sampled epsilons. Now, that's what I just said. If I define, instead of putting a prior over x, I put a prior over w. So putting priors over x gave me latent variable models. If I put a prior over w, that multivariate Gaussian rule immediately gives me this result. It tells me, if I put that prior over w, using the rule from before and this formula here, it says the mean, so if I put a prior over w that is 0 mean, the mean of the distribution over y will be phi times 0, so it's 0. If it's got covariance c, the covariance of the distribution over y will be phi times c times phi transpose. Because Gaussians are additive, adding that thing on will give me a plus sigma squared. So you see that on the next slide. C in this case is alpha times I, so the alpha pops out the front. So what this is saying, y, is drawn from a Gaussian distribution with 0 mean and a covariance with this interesting structure. Alpha phi transpose. That matrix, so why I love matrices is also things you can do to check. I told you this is n by h. So an n by h matrix, to multiply in this way, their dimensions must match. That's an n by h, but it's transposed, so it's h by n. N by h, I cross out the h's. This is an n by n matrix. That makes sense because this is an n-dimensional vector where n is my number of training points. Plus sigma squared. Sigma squared is just the noise. Two Gaussian random variables sum their covariances. That's all I'm doing there. But look at this freaky little thing here. Instead of putting a probabilistic model which is independent over my training data, I've said a probabilistic model, y, is drawn from a Gaussian, not the classical Gaussian where I have it independently across data points, but where every single data point of y is correlated with another one. Now, that seems a little bit alien to a lot of people. So let's just allow that to digest for a moment. And I'll take questions there at that moment. Any questions so far? But this is because this is like the big transition into the sunlit uplands. Any questions? Or we can just digest it if you like and reflect on that. If I got rid of the prediction function, if I hadn't done that Bayesian, this would just be noise, right? And now I've got this thing that's coming from the prediction function. Why I think it's weird is because people aren't used to looking at probability distributions which are jointly across their training data. And it freaks them out. But actually, that's the right way of thinking about probabilistic modeling, that's what you're looking to specify. Everyone then also thinks, oh, so this is Gaussian, so it must be uninteresting. Oh, and what's going on? How can it be 0 mean? Oh, my God. The mean's where everything is in the Gaussian, right? Why is it 0 mean? It's 0 mean because my prior distribution over the weights was 0 mean. So looking back on my basis set, the prior distribution over the weights being 0 mean, on average, the output weights, not the weights in there, sorry, that's a different set of weights, I should have probably got rid of that. The output weights here, that means on average, these cancel out. And that's why it's 0 mean, is on average, these cancel out. People get freaked out about being 0 mean. Why don't you put a mean in? Well, because the mean's not the interesting bit. You can put a mean in. People do put a mean in. Sometimes you should put a mean in. But it's not the interesting bit. The covariances, all the basis functions, all your modeling assumptions have appeared in the covariance. Notice that, yeah? Okay, no questions then. You all can go away and implement this then. Good. Now, oddly, the other interesting thing about this joint Gaussian density is if you look at the elements of this matrix here, they turn out to be a function of a number of things. They turn out to be a function of the activation parameters, your input layer weights. But in particular, they're a bivariate function of two data points. So the covariance between the ith and jth y in that vector, the elements there, turns out to be a function of the inputs of the ith and jth y. It doesn't involve any other input. The reason is because that matrix multiplication works out like that. I don't want to dwell on that too long because I'm behind already. Oh, there's the reason. There it is. This covariance function comes out of this basis set function. So the parameters are the same. These parameters are appearing in the covariance function. They're the parameters of your neural network. So, by the way, any neural network is trivially converted into a Gaussian process. Somehow it's still a paper, but it shouldn't be. It's sensible. You should do it, but do it when you've got a reason to, not just because you think you've discovered something magically new. So this is the elements of the covariance function. So what's going on? Instead of making assumptions about a density that's independent, we're making a joint Gaussian assumption. And that arises from integrating over W. Now, I said before, I cursed people for having parametric models. Where is the parametric nature of the model appearing here? Can anyone see how W still affects us even though we integrate it out? What's the dimensionality of this? N by what? Yeah, H, which is the dimensionality of W. So this matrix is at most rank H or N. If H is higher than N, it's rank N. But if H is less than N, as it typically is, fewer hidden units than data, this is a low rank matrix. So actually, if we don't add noise, this is a degenerate Gaussian. It's not a valid probability distribution. It's only when we add noise, because you can't invert this low-rank matrix, so you can't normalize the distribution. So our decision to have a fixed dimensional W is giving us a low-rank effect on this matrix here. And that's a limitation. And what you do in a Gaussian process is you say, no, I'll just make that infinite. And how do you make that infinite? Well, it turns out that instead of specifying the basis functions and then specifying W and everything else, you just choose to specify this thing directly. And you don't have an inner product here, you just have a bivariate function. As long as that bivariate function is provably positive definite, it's a valid covariance function. Now, that also, the classes of functions for which that is true is the same as the class of Mercer kernels. So now you see the overlap between kernel methods and Gaussian processes, because for something to be a valid covariance function, it has to be a Mercer kernel. And that object in the Gaussian just sits inside here as the covariance, relating the correlation between different points. Okay. I said that. So this was laid out really for the machine learning community by Radford Neal. He said, what would happen if you take H to infinity? And then he did some various derivations, and he sort of said, this is from his thesis. Distributions over the functions of this sort would be the joint distribution of the values of any function of finite points is a multivariate Gaussian known as a Gaussian process. They arise in many contexts, including spatial statistics, computer vision, and computer graphics. Now, what's also interesting about that is what he's proving there is something that is a little bit interesting. So I kept on talking about integrating out the W's, and I've done that. But what Radford Neal is proving is that if you put a prior distribution over this W as well, and integrate over it, and take the limit as h goes to infinity, and downscale alpha, you have to do all those things, that's still a Gaussian process. As long as the basis function, which is operating on this prior distribution, doesn't lead to a distribution of greater than finite variance. It's all based on the central limit theorem. The number of things you need to know to do this are like linear algebra, central limit theorem, and it's in Radford's thesis, and I would really advise reading it. It's a great piece of work. I mean, other people knew it, but Radford talks about it in ML terms. So I don't want to go through the details of that, but it's true that that's what works out. So it turns out that the way I can create infinite basis functions is I specify a probability distribution for my activation functions, and I create each one by sampling from my probability distribution for the weights, create a new basis function. I do that infinite number of times. Well, I don't, because I don't have to, because I can do the maths to show that that leads to something called a Gaussian process. And that's in chapter 2 of Radford-Neal's thesis, and you should read the whole of Radford-Neal's thesis and the whole of David Mackay's thesis, and don't do any more machine learning until you have done. No, you can do what you like. It's fine. Okay, so what does that lead to? Well, the Gaussian process, as I'll try and give you an intuition for as we go forward, gives you an ability to sample a function. These are functions from a Gaussian process, right? So I've defined a particular covariance function, and what I have to do, how do I do this? Well, I basically I construct a multivariate normal. Oh, I missed it. Oh, there it is. I'm just sampling observations y. Actually, I'm not sampling y because I'm doing it without sigma squared, and I'm using a classical kernel function I'll explain in a minute here. But I'm just sampling like 200 points from a Gaussian, and I'm plotting them against their input index. Yeah? And what you're seeing, so actually Carl Rasmussen always puts this very nicely. He says, what is a function other than a very, very long vector? Well, he doesn't quite put it like that. You know, a function is, in effect, f of x is, if you think of x as a continuous index on a vector f, then you can see that as you start moving from processes to functions. And mathematicians will be extremely upset with me, but I'm not a mathematician, I'm an engineer, so I don't care. And that's how I think of a function, as a sort of as just a discrete object that's indexed, as an object, a continuous object that's indexed by a continuous value, just like a vector is indexed by its element, its input element. And so all I'm doing to sort of sample these processes is I'm sampling on this continuous input space very, very finely, and then I'm just plotting the functions that come out. The other way of doing it, if I wanted to sample from a neural network, I could compute those basis functions. If it was a neural network, then I could sample from W and multiply it by phi. But that's not what I'm doing here. I can't do that this way here because I'd have to compute infinite basis functions. So I sample directly from the Gaussian. And infinite basis functions are special, right? What it means is, the way this one is constructed is the basis functions exist across the entire real line. They go straight through that mountain over there and all the way down to the Antarctic, and all the way up to the north and everything. They're everywhere. You don't have these weird problems of like, I've got 59 basis functions distributed across here. Wherever you see data, there's always basis functions present. Because the models, this model specifically is designed by sampling basis functions that are little exponentiated quadratic bumps and putting them uniformly, randomly sampled across the real line. Now, inferencing Gaussian processes requires you to combine, well, in effect, inference in any model involves sampling from your model of the world. What did I say? It's model plus data. This is the model. Here's 1,000 functions I've sampled from that. And now we're going to see some data. And in Bayesian inference, it's really very simple because you just multiply likelihood by priors and then do a very high dimensional integral. But when you look at it in this way, you can see it, there's a sort of, effectively, it's like a bit of like a rejection sampling. That if I throw away all the functions that aren't consistent with my data, and I just keep the functions that are consistent with my data, that gives me my posterior over functions. And I mean, conceptually, it's quite a simple operation. It's a conditioning operation. It's the P of y star given y. But it typically involves very, very high dimensional integrals. What I'm doing here is I've just thrown away any function that wasn't going through these points nearby. That is true of any sort of Bayesian inference process where you can sample from the process. What's remarkable about Gaussian processes is we can also compute that distribution over functions analytically. And you just get the most gorgeous things. This is the mean. This yellow is the mean. Now, be very careful with mean functions. The mean can be totally unrepresentative of the underlying functions. And in this case, you can see it is. Because these functions are sort of, they bend more. But there's an averaging effect here. Right? So people always look at the mean function and think, well, that's the best prediction. It's only the best prediction if you're going to use a quadratic error at the end. Many times you don't want to be using the mean. And you also, I'm showing here the marginal variance, but actually we have the full covariance structure. We can talk about the covariance between any point here and any point here. If you are low here, and with that gradient, you're likely to be high there, right? That structure is embedded in the Gaussian process. It's embedded in the covariance function. Not only that, these things are magical. You can, not only is the structure of the function, its gradient turns out to also be a Gaussian process. Its integral is also a Gaussian process. Everything is jointly Gaussian. That's not true of any other process. And I mean, another thing I think you'll also notice, most people are sort of expecting Gaussians to be noisy things. This is infinitely differentiable. This is another weird thing. It took me ages to get my head around this. There's a whole load of work in physics around stochastic processes and so on and so forth. And the first assumption is that the process is non-differentiable as soon as you made it stochastic. In fact, you could almost substitute the word stochastic for non-differentiable somehow. In this case, I've chosen a covariance function which has made these functions infinitely differentiable. They're infinitely smooth. That's actually can be a bad idea. I can make it non-differentiable as well. But I think that takes quite a while for people to grasp that you don't have to have, you can have a random distribution over functions that are smooth, because you just can. The reason people aren't so used to it is because the other main way of building stochastic processes is Markov processes, and Markov processes aren't smooth. So I think a lot of the work on stochastic process literature is from the Markov process perspective. Any questions at that point? Yeah, I'm doing well. You're all clearly keeping up. Okay, you can ask me questions in the break, whatever. So what's going on here? I want to just dive a little bit deeper into that. So what you're doing is you're sampling a function. You're specifying a distribution over functions. And so to sort of think about what that means, I'm going to, instead of sampling whole functions, I'm going to just sample 25 points from a multivariate Gaussian. So I'm going to sample one vector. Each of those functions was one sample. I'm going to sample one sample from a multivariate Gaussian. I'm going to plot them against the points of that sample against its index here. This is the covariance I'm sampling from, where black is high, unfortunately, and white is low. I hope that doesn't change later on in the slides. But black is high and white is low. So what it's saying here is that any 2 points that are close are highly correlated with each other, and distant points are not correlated. So when I sample the function, so there's the function, which involves, well, it's not a function. It's just a vector of 25 points. But it looks a bit like a function. And the reason it looks like a function is because these 2 points are highly correlated. In fact, if we zoom in, I've chosen a covariance such that, number one, the diagonal is unitary. So it means it's also a correlation. So the diagonal of this covariance is unit, and I've chosen a covariance such that the covariance between these 2 points here, the correlation coefficient is 0.986. So that's extremely high. And that structure is true for any 2 points I take that are neighboring along here. Now, what I want to do is show you what that looks like in terms of a Gaussian form. So now I'm plotting. This plot here is F1, which is the first of those 2 points, against F2, the joint distribution of the Gaussian, which is zero mean again, still zero mean, defined by this covariance here. This is one contour at one standard deviation of that Gaussian. So it's like a hill. I always think of this hill. That's not Gaussian shaped. That's actually a sigmoid convolved with a Gaussian. I always think of that because it's just sticking out of the surface. So, like, imagine you're looking at a probability distribution, yeah? I don't know what the side of Uluru looks like, and it's quite hard to find a picture of Uluru without a member of the British royal family standing in front of it, but in Britain at any rate. But looking at it this way, this is a one-dimensional distribution. If we were to look at it from a top, we could see it as a two-dimensional distribution, and we're looking at the contours of that, yeah? If you look, that view from that side there, that's actually the marginal distribution. So if you were down here, if Prince William and Kate were looking at the rock, they're looking at the marginal distribution of F2. And if I look from this side, I'm looking at the marginal distribution of F1. Now, the marginal distribution is found in a Gaussian. I forgot to highlight that point when we went through the last slide. Was that the last slide? The marginal distribution of these 2 points, that's kind of very unusual. I should have emphasized that. The marginal distribution of F1 and F2, to integrate all these, I'm just a 23-dimensional integral, right? To get rid of F3 to F25, right? That's normally hard. If I do that on a typical probability distribution, a lot of integration work ensues, and most distributions I'll have to do sampling or variational approximations. Here, it involves just looking at the relevant elements of the covariance matrix. Now, I think the 2 reasons that's true about a Gaussian, that I can integrate by just throwing away rows and columns of the covariance matrix, as I'm doing here, to look at the marginal distribution of that. That, plus the fact that I combine Gaussians by summing the covariance matrices, means that the covariance matrix is the fundamental object of the Gaussian, right? Now, a lot of people will say, and I would agree with them. Go ahead. Yeah. So you've got one-to-many, so you've got more than one output in the function. So you need to do something non-Gaussian. So you would need to use the Gaussian process to drive either a mixture distribution, or the other thing that people have done, including myself and others, is use mixtures of Gaussian processes. So you decide, oh, sometimes it comes from one process and sometimes it comes from another. How do you decide how many? Well, you do a lot of integration and compute the Bayesian marginal likelihood and select the one. In theory, in practice, you might have to do all sorts of things like cross-validation or something like that. It can be quite hard, that type of analysis. Other questions? Okay, so I'm down to this marginal. I'm representing that marginal distribution of F1, F2. Now, oh yeah, the point I was making was that the covariance is it's like the API of the Gaussian process. The reason you could represent things in terms of precisions. Precision matrices are very interesting. If you have a Gaussian random field, the precision matrix will reflect the sparse structure of your Gaussian random field. The conditional independent structure is in the precision matrix, the inverse of the covariance matrix. Sometimes called the information matrix. So that's a great matrix. But if you want to combine 2 Gaussian processes and you've defined them both in terms of their precision matrix, you have to first invert their precision matrices, then add them together. And then the thing you add together typically won't be sparse. So that's why sort of sparse, like Kalman filters, are not trivial to add into other Gaussian processes unless you compute their covariance function, which you can do. So the Gaussian, the problem with that is that as soon as you map everything to covariance functions, everything will turn out to be computationally cubic in the number of data and quadratic in terms of the storage. And that's the headache of the Gaussian process. There's all this wonderful, feely good stuff. And then when it comes to it, if you want to use them in their most general form, you have to keep representing these covariance functions. In practice, there are many, many things that are Gaussian processes that people are using that they're not even aware are Gaussian processes, like Kalman filters. Which have very efficient algorithms associated with them and never represent themselves in the form of the covariance. They represent themselves in things like conditional probability distributions. Also, the whole of classical signal processing with Nyquist stability, it turns out that a band-limited signal, if you make an assumption that a signal is band-limited and the energies are uniform, that's a Gaussian process prior. It just turns out that that particular assumption allows very, very quick computation. There's all sorts of things you can do to get quick computation, but in general, it doesn't exist. Sorry, where were we? Uluru. I can't pronounce that very well. Uluru. Arthur's not here. It's all right, isn't it? Good. Okay, so what goes on? How do we do inference? This is the joint distribution of F1 and F2. And what I said is, in the world of probability, prediction is just conditioning. So what if I want to make what if I've observed F1? So this is the observation I had for F1 in the previous picture. And so I've drawn it as a line along the F1 axis. And what if I want to make a prediction about what F2 is? Well, it turns out that that conditioning operation in a Gaussian, that this conditional probability is also Gaussian. And it turns out that a good way of thinking about what that Gaussian looks like is to imagine you're slicing through Ayers rock along that. Don't do it. But imagine you're doing it along that axis. And the profile of where you slice down, that's going to be the profile of the new probability distribution. That's true of any conditioning. But this funky shape of this elliptical shape, that shape is also Gaussian in the Gaussian process K. Again, it's not normally, if you take that for a general distribution, that won't be the case. So imagine I'm slicing through there, then the slice through I get has what I call the exponentiated quadratic form. And if you renormalize it, you have to renormalize it, because, for example, if you're down here, there's hardly any rock, so you have to scale everything back up again. Then what you see is a distribution like that. So what this is, the conditional distribution over F2, given F1 is at this level. Because things are highly correlated, when F1 is negative, F2 is also likely to be negative. The mean is close to the value of F1. It's somewhere around here. F1 is somewhere down here. It's a little bit towards 0, actually. And then there's some little variance associated with it. If the correlation was 100%, this would be a straight line, and that would be a delta function, and that would be like a degenerate process, because it's not a valid probability that's coming out. So 100% correlation, as you drive this towards 1, you would find that F2 is equal to F1 with 100% probability. Any questions about that? So that's the sort of mental model of what you're doing with your Gaussian process. Of course, you don't do it mentally, you do it in maths. And this is what the formula looks like, that you've got those elements. This is 1 and 1, this was 0.98. So that's 0.98 over 1. So the probability distribution of F2, conditioned on F1, is 0.986 over 1 times F1, a little bit smaller than F1. And the variance of that object is the prior variance, K22, which was 1, minus the square of the 0.986. So minus 0.98, if that was 1, that would be minus 1, so the variance would be 0. So 0.986 squared over K11, which is 1. Now that's for 2 data points. In general, in Gaussian processes, you can do it in matrix form. So what's interesting for me about this is if we go out for the 5th point, it's also correlated, but it's more weakly correlated. So if we go through the same little analysis, we do the same thing again. So this is the 8th point. I thought it was the 5th. Let me count that. That's funny. 1, 2, 3, 4, 5, 6, 7, 8. Okay, it's the 8th point. So this is the 8th point away. Now it's got a more diffuse, a fatter probability. And if we look at the conditioning, we put the value of F1 in again, we look at the conditional, it's very, very wide. In fact, it's halfway, because remember, that's going to be, that mean location is going to be 0.506 divided by 1 times F2, so it's halfway back to 0 already, the mean. And the variance is sort of really blowing up, because that variance is coming from 1 minus 0.506 squared, so that's 0.25, divided by 1. So it's 1 minus 0.25, so that variance is already 0.75, square root 0.75, up round point something, I don't know. That's the limit of my maths, I can't do square roots on stage. So it's much broader. So even though the correlation coefficient is quite significant, people will get excited about that correlation coefficient if they were statisticians looking for correlations. It's sort of really diffuse by the time you get 8 points away. So one of the things that should give you an intuition about is the form of the process itself is defined much more in the region where the correlations are close to the diagonal. And that's one reason why covariance matrices are often very not an intuitive representation, because a lot of the things you're interested in, not the length scale is kind of obvious, but a lot of the properties of the function you're interested in aren't very obvious in the covariance matrix, because they all occur in how the covariance increases or decreases as you move away from each individual point. So other representations are sometimes more helpful. But the covariance is like, as I say, it's the standardized thing. So it's the key object. It determines the properties of the samples as a function of x. Okay, these are the matrix forms if you're doing multivariate. So if you have more than one training data point, I do love it when you have one training data point. With Gaussian processes, you can work with one training data point. You get matrix form equivalents of those things. So instead of now this is a vector computed, the cross covariance between the test data that you're interested in and your training data, the inverse of the covariance matrix of your training data times your training data. That gives you the mean. That turns out to be like a kernel smoothing of your data. And then this covariance matrix itself has this structure of your prior covariance of the test data minus the cross covariance between the test and the training times the inverse of the training, blah, blah, blah. All those forms come out just of conditioning Gaussians. The thing to note about them is this thing that they have in the worst case cubic complexity because of the inverse. Well, it's not even the inverse. If you're multiplying 2n by n matrices, that's cubic as well. And quadratic storage, because you have to store n by n data, and that's a headache. We have techniques that I'll briefly touch on next time for trying to deal with that, but that's the sort of headache that we have. We have all this elegance, and then, of course, nothing's as simple as that. So we can't do billions and billions of data yet. Okay. So that's the formula we use to derive this. So those things are just coming from me operating those formulas. Oh, and by the way, in rough form, all the slides are online, an enormous notebook which tries to, I'm not sure if it's properly linked yet, which goes through this a bit slower and explains some of these things are online as a resource. Now, unfortunately, I'd failed to fix these things, but I just wanted to show you the sort of, all of these are going to be dropped down here, unfortunately. But different covariance functions, this one I call the exponentiated quadratic. I was pleased to hear Arthur calling it that as well in his lectures. Sometimes it's been called the Gaussian. It's not a Gaussian because it's not normalized. And it's called the squared exponential sometimes. It's not a squared exponential because it's not a squared exponential. So to make fun of it, I called it the exponential quadratic and keep calling it that. It's this exponentiated quadratic form. So what it says is as the squared distance between points increases, the correlation between any two points decays, and I was worried that was going to happen. So the correlation is maximized on the diagonal when the points are the same. As you go off diagonal, the correlation decays. And that's what's giving us these functions here. And this representation of these functions is an idea due to Philip Hennig again. It's coming from looking in the probability space of all these functions and sampling one function and then taking a tour around on a contour of constant probability in the infinite dimensional space that function represents, taking a great circles tour. It's just a lovely, we're going round the world of probability, and it's quite easy to implement using sines and cosines. And you're just seeing the nature of these functions and what they look like. And what I like about it is you can see a little bit the stiffness of these functions. They're very stiff because they're infinitely differentiable. So they're often, in high dimensions, they're fine. In low dimensions, they're often a bad idea because as you get data closer and closer together, this is too stiff, it's too smooth. Not many data is this smooth. But nevertheless, it's quick to compute and quite widely used. What does that say, 10? Okay, good. Okay. Anyone here from Uganda? Nice. So who's this? Well, it says up there, doesn't it? Who is it? Stephen Kiprotich. So he won the 2012 marathon in London. And the first time I gave this lecture was in Uganda. And he's only the second ever gold medalist from Uganda after Aki Boer in 1976. And anyone here from Kenya? Yeah, they know what's coming next. So, of course, he beat a load of Kenyans. So what I want to do is just sort of show you a little data set taken from Marathon Times. And I like this data set because in 1904, the Americans held the Olympics, and the marathon runners got lost. So it's got an outlier. Only 6 people finished. Like, I can't run a marathon that quickly, but, you know, if I really trained, I could. I'm like about here or something. But that day, they got lost. They had cars. It was a nightmare. Anyway, I can't run a kilometer that quickly. And that's Stephen Kiprotich's speed. It's just absolutely shocking. So these are marathon speeds. So I like this data set as a sort of one just to apply a Gaussian process to. And I'm going to use it next lecture when I go to deep Gaussian processes. So what I'm going to show you is what happens. Oh, this is another thing I love about marathons. Alan Turing, you know how fast he could run a marathon? 2 hours 46 in 1948. This is the results of the Amateur Athletics Championships in 1948. He came 8th in Britain. And bear in mind that Britain, in those days, had good marathon runners. So he would have been probably around about here. So you want to know the probability that Alan Turing would have won the Olympics had there been one run in 1946 in that year. So that's actually an interpolation question. Okay, and so how do we do that? We want to fit some sort of model of how we think marathon times are evolving. Now, it's going to be a very simple, dumb model, okay? And it's not going to work that well. But that's the sort of thing we might want to answer. So we'll do that. We'll fit a Gaussian process to this data. And this is what it looks like. And of course, it doesn't look great because there's a number of things going wrong. And we'll try and deal with them in next lecture. There's a number of things you can do to deal with this, right? So this is an outlier because of bad running of the Olympics. And if you remove it, things clearly get better. I mean, you can see some interesting structure. It looks like things maybe did they tail off? I don't know when they didn't run marathons during the war, seemingly, perhaps. Who knows? It's very difficult to sort of say exactly what's going on. Also, there's something, you know, here it seems marathon times are much more consistent. But yet we've picked up a variance which is more appropriate for here and is taking in that outlier. So all sorts of things go wrong. When you start dealing with uncertainties, this is much more noticeable than when you're not dealing with uncertainties, when you're just fitting a straight line. If we'd taken these uncertainties, these error bars away, then you would probably think that that was quite a reasonable fit. I mean, there's things you can do to get rid of this. You can try and deal heavy-tailed noise. But we'll show you, I'll show you next time a way of getting rid of it. Because one of the things I'm going to propose is that deep Gaussian processes help with this. So deep Gaussian processes are putting one Gaussian process into another. And I'll talk about that a bit next time. There were parameters in that covariance function. And the question is, can you learn those parameters from data? And the answer is you can. So this is the likelihood of a Gaussian. And I want to split it and you to focus on these two terms. This is the determinant of the covariance matrix, and this is actually like a data fit term. It doesn't appear like a data fit term to the uninitiated, but what it is it's a quadratic form. So it's an enormous quadratic well, right, centered at 0. That's why it doesn't appear like a data fit form. And the data points, this is a quadratic well in n dimensions, and this data point y is a point in n dimensions in that quadratic well. The closer on that quadratic well declares contours, right? So that if the data point is low down in those contours, this data fit term is low, and it goes down to a minimum of 0. This term here is it's the footprint of the Gaussian. It's the normalizing coefficient of the Gaussian. So in order to normalize, this represents like the volume of that covariance. So those two terms, I mean, it's just the likelihood. There's nothing fancy going on here. We didn't write these down a priori. I'm just trying to give you some intuition for what goes on. Those two terms, when you fit to data, allow this sort of thing to happen. So I'm changing the length scale of the process. The length scale is how quickly these functions wobble. People would say, oh my God, it's overfit. It hasn't overfit. It's just saying I have no idea what's going on. The mean function, if you rely on the mean function, it looks like you're overfitting, sure. But all the mean function is saying, I know nothing apart from it's somewhere close to those data points at this time. When people tell me the Gaussian process is overfit there, I have to resist punching them. I don't really. But it's a real misunderstanding. If it was a standard kernel model, that would have overfitted. But here, all it's saying is, the only thing I can tell you, given the scale at which this process is varying, is that when I'm near these data points, the mean is somewhere close to those data points. Now, what I'm going to do is I'm going to increase the length scale, and I'm going to show you the decomposition of the error function. I've called it the error function, which is the negative log likelihood, dropping some constants. I'm just going to show you it in terms of yellow curve, cyan curve, and another color curve, green curve, which represents the likelihood itself. And you'll see that as we change the likelihood, that was too quick. Let's go back. As we change the length scale, what happens slowly is the data fit term starts to improve, and then it gets worse. So that's the cyan there. It improves a little. So the data fit term At that point there, interestingly, it is now interpolating exactly through the data. So the data fit term does improve and then goes off again. But look at the capacity term. The likelihood itself, which is the green curve, is being driven by the capacity term. So the capacity term is getting much better. At this point here, the capacity term is too large. Because that's the entropy of the Gaussian, what it's sort of saying is there's too many functions under this thing. There's too many things. I mean, we're fitting, but there's many, many functions here, right? As you change the length scale, you can't count the functions because it's a continuous process. But conceptually, that's what's going on. It's saying I can count too many things going on here. In my engineer's mind, that's what I think of going on. And then as we increase, we eventually hit a minimum, which was actually at the length scale 1. So we keep increasing the length scale. The data fit term gets really poor. The capacity term keeps improving. Because the capacity term, now this is saying this is just noise and a constant function. So basically it's one function. So the capacity term loves it. The capacity term, this is fantastic. There's really only one function plus independent noise here. But the data fit term says, no, that's not good at all. And these two terms working together to give us the ability to actually determine the length scale. And since I generated this data, I do happen to know the length scale is 1, so that is the correct answer. Look how beautifully the error bars expand as you leave the region where the data is. They don't do that on neural networks. And genuinely, if you see them doing that, it's quite likely they fudged it in the data. I mean, I've never seen an example. Fixed basis functions just don't do that. Be very suspicious of results where you see them doing that. Unless they've done something really clever. It just doesn't come out like that. Okay, so just a couple of examples. Here's one. This is a gene expression experiment. I don't have much time, so I'm going to go very, very quickly. This is gene expression data over time, and I was working with a PhD student. We were interested, is there any signal in this gene expression or is there not? Who thinks there's signal in this gene expression here? 12. Who thinks there's no signal in this gene expression? Who doesn't know what gene expression and signal are? So gene expression is the level of a particular gene in a cell over time. So this is a signal, it's a noisy signal, and we're interested, is this a gene we should look at as being involved in this process? And as you say, it's pretty hard to tell. Well, let's look at a few Gaussian process fits. So this is what we did in this paper. Here's Gaussian process fit 1. Isn't it nice? It's saying it's quite high noise, but there is some signal. We were trying to evaluate by signal to noise. In a Gaussian process, that's very easy to compute, the signal to noise ratio. It's a common thing in engineering, using the covariance function we use. And so this says there is some weak signal here. The likelihood of this is minus 16.6. Here is another fit. This says there's no signal, and the whole thing is noise. The likelihood of this is minus 18.4. It is entirely valid to do a likelihood ratio test to compare between those two possibilities. And it tells you weakly, I mean, there's a difference of 2 or something, so that would be like e to the 2 more times probable there to be some signal than none. Interestingly, and this is one a bit of a nightmare about optimization over covariance parameters, that fit is almost exactly the same likelihood as the first fit. Okay? So be very careful. This fit is also very valid. What does that mean? One could say this has overfit. I would argue this has overfit in this case. Why? Because if we look at the error surface of the two parameters I'm fitting here, one is the signal-to-noise ratio, the ratio of noise to variance. I've taken the overall scale out of this plot. The other one's the length scale. That mode there is one sort of, it's the mode where it's not very much and high variance, sort of the signal-to-noise ratio is about 0. But there's another mode all the way up there. And actually what you need to do in this case is sample over your covariance function parameters. You do not have, the height of this mode is minus 18, the height of that mode is minus 16. You do not have enough evidence to choose either of those things. They're all valid. What we do know is that the example where, having said all that, the noise-only example can be kind of rejected because all these modes are lying where there's signals. So for our cases, it was fine. But in this case here, this is an example where there's not enough data to properly determine two of those parameters, and you start needing to do another level of Bayesian inference. Okay, just some final examples which are from Uganda. So this is an image of Uganda. This is late Victoria. Some of these islands belong to Uganda. Some are in, there's Kenya there. There's Tanzania there. And we were interested in malaria across Uganda. Now, it's very common for spatial data. Spatial data is like, it does worry me the more I see machine learning talks and the less I see about spatial data, because it kind of tells you that the entire community is utterly disconnected from real-world problems. Because something like, to my mind, I don't know, I'm going to make it up, 30% of real-world problems turn out to be spatial problems or spatio-temporal problems. So it kind of means that machine learning is ignoring an enormous number of problems. Anyway, this is a spatial data problem. Comes up a lot in spatial statistics. Gaussian processes are quite widely used. We're interested in the distribution of malaria. Now, I just wanted to start with this. So if I got that right, I think that's where Stephen Kiprotich is from. It's quite close to Kenya. So there's different districts, and we're interested in malaria reports in those districts. So malaria reports are made by different health centers. They're recorded in something called the HMIS data. One of the problems with spatial data in Uganda is President Museveni every so often sees fit to take one of these districts and split them in two. That's clearly for administrative reasons and not so that he can give a lot of jobs to someone in a new district. But it does happen rather more in Uganda than it happens in the United Kingdom. That really messes with a lot of spatial statistics techniques, because all those conditional probability things, Gauss random fields people use, get broken apart. So that was one reason for being interested in Gaussian processes here. In Tororo district, there's something called a Sentinel site. It's a site where the World Health Organization monitors malaria. And what we were interested in is, could we use Gaussian processes to relate the sort of values we're reading at these Sentinel sites of the all patients with malaria, the HMIS patients. The HMIS patients are the ones we're getting from the other data source, which is less well qualified, with weather station temperature and satellite levels of rain, all these things we thought might be correlated with malaria. So, here's the Mubende district, and this is something where we are bringing in some of those correlations. So this is not a strong result, by the way. I'll give you a reason why this isn't a strong result. This is without correlating across the different central districts, and we're getting a little bit more signal when we are correlating. Look at a number of things that are going wrong in terms of those variances before. This is not a final piece of work. Modeling in the real world is hard. The most difficult thing about this turned out to be that the data we were looking at had been agglomerated without accounting for missing variables. And we weren't able to see that until Ricardo, my student, spent 2 or 3 months in UN Global Pulse in Kampala and was able to look at the disaggregated data. Once he'd done that, everything worked better. By that time, his thesis was done, which is it shows you how close you have to be with the data. Because Martin Mubangizi, who we were working with, who was the Ugandan student working on this, he was doing loads with the data. He couldn't see that. So the whole thing kind of didn't fully work until after the thesis was finished, when Martin actually got very close to the data when it did start working, because there was an agglomeration of data with missing values from the different health districts which we weren't aware of. And that type of agglomeration destroyed spatial structure. So if you are working on Ebola data from London in the UK, I seriously question whether you're in a position to really make strong statements unless you're very well connected with the people on the ground. Okay, we had a Gaussian process summer school in Makerere, and that's actually what triggered the whole Data Science Africa thing. That was a small starting one. So what did he turn it into? Well, I think it still runs at the Ugandan Ministry of Health. This is one idea: health monitoring systems that are showing what's going on. So now this system here is showing you a couple of different interesting things. So it's monitoring, once we got all the missing data stuff dealt with, the malaria levels over time. And it's using a process with 2 different length scales. One is a slower varying length scale, the red line. The other is the rapidly varying blue length scale. And what you are visualizing, I think Ricardo took this from the economics literature here, is some different colors. If it's in this square, it could be a circle, but he made it a square. If it's in this square here, then it's just gray. If it's here, it means that the average malaria is low and decreasing. If it's here, it's below average but increasing. If it's here, it's above average and increasing, because we can get the gradient out of the GP as well. It's a joint GP. We could even do this with uncertainty. If it's here, it's above average but decreasing. And then what you can do, and this is the sort of thing that I do think is valuable, is convert that into a map that gives you an early warning system of what's going on in the districts across Uganda. And if you're seeing that directly, taking in with all the missing values, then humans can take action. Okay, I'm out of time. I was just going to show you some different covariances, and the fact that this cover of this book, that's a Gaussian process analysis of birth rates done by Aki Vatari, and it's using a additive covariance function to get a lot of interpretation about how birth rates are varying on a day-by-day basis, how birth rates are varying on a weekly basis, all the seasonal aspects. It's a lovely piece of work, and it's so lovely that it made the cover of the most recent edition of Gelman's book. So I'm out of time there. There was just at the end, the Gaussian Process Summer School. We have our GPy software for doing Gaussian processes. There's other software people have developed based on TensorFlow called GPFlow, and more recently GPyTorch. None of them are as good as our software, which is much, much better. But we do concede that the probabilistic programming is a real revolution that allows us to do some interesting things with Gaussian processes. And we've written a probabilistic programming language called MX Fusion that is based on MXNet, that is targeted at Gaussian processes, doing the sort of things I'm going to talk about next time, and integrating neural networks in those analyses as well. So that's it. Thank you.